Okay. I'm going to talk very briefly. In the interest of time, I'm going to skip some of this material, because my guess is that this group is more interested in. You know what I'm going to do? I'm going to actually go to the stuff. I'm going to reorganize this talk. So I didn't sort of think about this in terms of people trying to catch a plane. I went through all of this stuff at the beginning about empirical Bayes, and that was actually going somewhere, and this is where it's going. So I said at the very beginning that dynamic factor models are just one of a possible set of ways you could approach this, that there's a whole family of different procedures, and that the whole reason of going through that empirical Bayes was there's very sound theoretical reasons to think about alternative procedures, not just DFMs. So before one just says DFMs are great and you go on your way, it really is incumbent upon everybody to look carefully at all of these alternatives that are theoretically suggested. And so this whole set of slides has to do with forecasts based on Bayes and empirical Bayes methods. And I will come back to that because I think this is quite important. And in the bottom line, it ends up making dynamic factor models looking very promising. But I'm going to come back to that empirical evidence on dynamic factor models and their forecasting performance and their fit, which is a substantial amount of work. But I'm going to do that at the end because I have a feeling that there's probably a fair amount of interest in talking about applications of DFMs, first of all as in the context of structural vector order regressions, second in the context of IVs, and third in the context of DSGE estimation. So I'm going to talk about those three topics, and then I'm going to return at the end to topic 5. It's not exactly the logical order. A logical order here is before just jumping on board the DFM bandwagon here, we really should test it against a lot of other things. It turns out it does really well. Okay? So we'll come back and we'll give that evidence. Okay. FAVAR. So far what I've been talking about is using DFMs solely in the context of forecasting. We've been interested in the space spanned by the Fs, and if we had the space spanned by the Fs, we can use that for forecasts. And I mean, that's a very interesting application. If you think about it, we can have internally consistent forecasts for a large range of different series. We can do it on a daily basis or a weekly basis. You can have a completely consistent updating system when data revisions come out, and it sort of incorporates all of this stuff in a completely coherent way. So that's very appealing. And I think that's a really big triumph of extensions of time series technology. Without imposing any structure at all. It is that said, many of the questions that one is interested in are structural questions, such as the SVAR impulse response question about the impulse response with respect to a monetary shock. Okay, so you remember all of those critiques from yesterday about SVARs, and FAVARs are an attempt to get at some of those critiques. So, you know, how Rudebush and others pointed out that the Fed uses more information than is in a standard VAR, and that's just true. It's completely true. There's this question about the invertibility problem, whether or not the space of the structural shocks are spanned by the space of the innovations. And then there's the question, even if only you want to use a VAR for forecasting, you might want to be able to use an extension of a VAR with lots of variables, but not necessarily in the dynamic factor structure. And so an attempt to address these different concerns has been to try to take some of the technology from dynamic factor models and pull it over into the SVAR literature. So that's there's a bunch of papers that have done that. They all differ. And there's other ones I'm sure that I haven't listed. They all seem to differ in the details of the implementation. I don't think there's any when you sit down to the level of the specific steps in the algorithm or the computer program, everything is a little bit different. I don't think this is a convergence on a single method. What I'm going to describe here is something that's very similar to the original, the key paper in this literature, which is Bernanke, Bovan, and Giannoni, and Bernanke, Bovan, and Elias, BB&E, not every detail is the same in the way I'm describing it as in BBE, but this is the general idea. All right? So, here's what we want to do is we want to identify a structural shock, and we want to use this to produce impulse responses for a large range of variables. So we got to deal with the identification problem. So we somehow need to formulate this in a way that we can attack the identification problem. You can't just like throw in the Fs as regressors. The Fs are not identified, right? The Fs that we've been using so far are unidentified. There's an arbitrary normalization. In the way they've been constructed by principal components, it's not a Kleski factorization. They're orthonormal by construction, but it's because of this eigenvalue thing. I mean, it's totally arbitrary, right? It's a totally arbitrary normalization. We've got the space spanned by the Fs, but we sure don't have any structural shocks. So we're going to want to, if we want to think about those Fs in a meaningful way, we're going to have to somehow do some identification. The Favar approach, let me just step through this. Right? Let me step through it. All right, so here's, I'm looking at a DFM with first-order dynamics. Right? So it's easier without lag polynomials. All right, so first-order dynamics, so the static factors obey a first-order vector autoregression. These are the shocks. Let me use the better word. These are the innovations in the dynamic factor model. The dynamic factor model innovations, there's only Q of those, but there are R static factors. So G is a R by Q matrix, which takes the reduced number of dynamic factor innovations and turns them into innovations to the static factors. The static factors then enter into the X equation, and I'm going to assume first-order dynamics for an AR1 for each of the E's. So it could be higher order. The fact that these are AR1s and VAR1s makes no difference at all, but it just makes the exposition simpler. Okay, so what I'm going to do, the first step is I'm going to turn this system here, which is a state space representation, into a VAR, something X here. Here's the X depends on current F. I want to get rid of that, and I want to just have it depend on shocks and lag stuff. All right, so I'm just going to do a little bit of algebra. The way I'm going to do that is I'm going to first quasi-difference the X's, and then I'm going to substitute this the F equation in, and then I'm going to rearrange everything, and then I'm going to stack it with the F equation, and here it is. So it says that the F's depend on lag F's with this F. This first equation is just the state equation for the F's. The second equation is that X depends on lagged F's and lagged X's, and then some innovation type things. So this is the innovation. This is the innovation, the disturbance type things. This is the innovation in the factor equation, and this is an error term or a measurement error, if you will, in the X equation. All right. So now how does this relate to usual VARs? The residual or the innovation in a conventional VAR, which is the projection of X on itself, well, throughout all of this, like I did at the beginning, I'm going to assume that the factors are observed. Why am I assuming the factors are observed? Because we can actually estimate them consistently. So for the sake of this argument, let's just imagine the factors are observed. So the projection of X on itself is equivalent to the projection of all of X on the factors and itself. And so if that's just going to be these bits here, it's going to be lambda times g eta t plus zeta t, where the zetas are the disturbances to the idiosyncratic process. Okay, so with that setup, we're now ready to ask this identification question, and the identification question is what's the relationship between the innovations in the dynamic factor model and the underlying structural disturbances to the dynamic factor model. This is the exact same notation. This is now an eta instead of a u, but this is the same business as yesterday when we were talking about SVARs. What's R? Right? So that's the identification question. And at this point, you can start talking about identification in a variety of different ways. But the way that, I'm sorry, let me postpone that just for a second. Once I know that rotation, matrix R, I could then compute the impulse responses. So I substitute everything in, and I just write things out in moving average representations. And this is going to be the impulse response lag polynomial, or this is just going to be the impulse response matrix. That's what I want, which is going to be the effect on the x's of an impulse response to the epsilons. Okay, so lags. I just wrote out in the formula in case there's lags there. And so the main issue is what do we do in terms of identification? And at this point, actually, I think the easiest thing of all to see is this idea of Herold's, which is I've got this system now, and I can actually I could say that this has a covariance matrix that's the identity matrix. I can identify the space spanned by the etas, so I can come up with R that's going to be a Cholesky factorization of the covariance matrix of the etas. And I can just go through and I can say, I only want those R's that satisfy certain sign restrictions. Okay, so the easiest way to think about identification here without having to do any complicated projections or anything is just to say, I'm going to go sample R after R after R that's going to be a rotation of a Cholesky factorization, and I'm going to keep the ones that have impulse responses that look good. That's probably not a fair way to say it, but that satisfy a priori theoretical restrictions. But actually, you can work through the algebra and you can do heteroscedasticity here too if you wanted to. Now, what BBE do, I actually haven't worked through the algebra on long-run restrictions. I bet you could do that, but I haven't done that algebra. What BB and E do is they do a timing scheme, a slow, fast timing scheme, just like we set out in the handbook chapter by Cristiano, Eichenbaum, and Evans. Let me talk about that just briefly, okay? So here's the idea. This is not actually how they implement it. This is how I understand how I would implement it, which is you categorize the variables into three groups, into slow variables, a policy variable, and fast variables, and then the factors are completely unidentified. But what you would posit is that one of the factors is actually a monetary policy factor. That monetary policy factor isn't necessarily observed. There's some measurement error on it. So what you'd like to know is you'd like to know the eta t of the monetary policy factor. With this fast-slow identification scheme, some of the factors are going to be loading contemporaneously on some of the factors. I'm sorry. The restriction is that the monetary policy factor does not load on the slow-moving variables. So here's the idea. You take the VAR residuals for the implied residuals from the structure for the slow-moving variables. You do a reduced rank regression of those onto the space spanned by the etas. You then take, now you've got the space spanned by the etas, and space spanned by the etas and also the space spanned by the slow-moving variables. You can then use the exclusion restriction that the interest rate shock does not enter the space spanned by the slow-moving variable etas to identify the interest rate shock in a completely parallel fashion as to how you would do it in a regular timing VAR, and therefore you have the eta TR. And so you got eta TR, and then you zap it through. So that's in words. That's not exactly how they do it, but that's described in more detail in a Stock-Watson 2005 paper. Okay, and the thing is, like, you get oodles and oodles of impulse responses out. And also what's kind of interesting, and I think this is a good question, and what part of the point is that you're using a lot more information, so you should get more efficiency. And maybe that means that the fact that they have tight confidence bands here is actually correct. I mean, it's plausible that you're going to get more efficient estimation of all of these things by using a much bigger system. And you could just go on for pages and pages in terms of impulse responses because you've got so many variables in the system that you can actually tell a story about what's happening to every variable that you could want. Okay, one other important point that's, I think, quite nice about this structure is that we're used to thinking about structural vector autoregressions that are exactly identified. This is way over-identified. There are a ton of exclusion restrictions because there's a ton of slow-moving variables, and we're saying that those interest rate shocks don't enter any of those slow-moving variables. So you can go through and you can see, well, does that look credible or not? I mean, you can estimate, you could put those in the regressions, you could see what the coefficients are, you can do J-tests, but you can also just see, is this a big deal or not? Do we believe these exclusion restrictions? So that's kind of a nice feature, that you could do SVARs that aren't exactly identified. So there's a lot of nice things about this, actually, very intriguing. Okay. Factors as instruments. I guess let me just make one quick other comment about favors, which is, as this list indicates, I think there's a lot. I haven't seen any paper that's done any of these three items. So I think there's a lot of interesting things to pursue here. Oh, there is one with sign restrictions? Oh, whose? Oh, okay. Is this an uncirculated paper? So it's all right that I didn't know about it. Okay. Okay. There will be a paper on sign restrictions in favors. Good. I'm a good forecaster. Okay. Factors as instruments. Okay. In some sense, this is all going to be just an application of theory that's already been presented. Remember, in the Stock-Watson 2002 and then refined in the Binding 2006 paper, theorems were proven that indicated that you could use the factors as regressors in forecasting equations without having to worry about a generated regressor problem. Basically, you're estimating them well enough that you could just throw them in as data. And, a forecasting equation sounds a lot like a first-stage regression. And so if you can do it in a forecasting equation, you ought to be able to do it in a first-stage regression. And so that's what this literature is about. This is not actually all that new an idea. So I understand that this was done like 30 or 40 years ago by the simultaneous equation folks who would have lots of instruments and they didn't know quite how to use them all. So they would compute a principal component and they would just use that as an instrument. So there's no theory or anything like that, but it's actually not new to knowledge. Certainly the proof about how this actually works is new to knowledge, but it's not exactly a new idea. One of the interesting so the whole point of this, going back to weak instruments, the whole point of this is, we're not so in some applications. Some applications, instruments are strong and GMM works great and we're happy. But in some applications, we just don't have strong instruments. And in those circumstances, there's some technology that's available for improving the quality of inference with weak instruments, but it sure is a nice idea to try to get better instruments. And so that's what this is about. Maybe this will produce better instruments, stronger instruments. The main theorem, which is in both of these papers, there's two independently written papers that were written apparently within a week of each other by Capitaneos and Marcelino and Bai and Ning. And the main theorem that they both prove is that you get first-order asymptotically equivalent results under the usual conditions with many instruments. That these are going to be, it doesn't matter whether you use the true factors or the estimated factors. And, before we were talking about the many weak instruments problem, and we were talking about many instruments, like k tends to infinity and k over t to the fourth tends to 0. We're talking about tons and tons and tons of instruments here. But the reason this isn't a many weak instruments problem and that technology and that constraint doesn't bind is that, of course, the linear combination that you're using isn't being estimated in a first-stage regression. The linear combination is being estimated through principal components, and all of the action is coming through the dynamic factor structure. And then once you've got a small number of instruments, 2 or 3 or 4, then it's just standard. It's no longer a many instrument problem. Okay, a couple of interesting notes on this. This is, I think, I can't think of an application off the top of my head for which this is a useful comment, but it's an interesting comment. So the interesting comment is that under this dynamic factor structure, any individual x might not be a valid instrument, but the principal component formed by the x's might be a valid instrument. How can that be? And the reason is if the idiosyncratic terms are correlated with the error in the equation of interest, you essentially average out the idiosyncratic terms and you're only left with the factors. So if the factors are valid instruments and the idiosyncratic and the individual ones or individual x's are not because of the idiosyncratic terms, you can get rid of that endogeneity using principal components or by this factor method. So that's an interesting point that helps you understand what's going on. I can't think of any application in which that's a useful observation, but maybe there is one. This doesn't solve this. The hope here, of course, is that this would solve the weak instrument problem, or at least it would solve it in the sense that you wouldn't have to worry about it. That may or may not be true. That might be a false hope. If it's a false hope, then if these factors are weak instruments, then you're still back in the first of my talks. DSGEs and factor models. Any questions on that? Okay. Well, when we talked about factor models yesterday, the steps were solve it for the Euler equations, log linearize, solve for the expectations, put it in Statespace Form. And that Statespace Form for that's, for example, that's what Sargent did. He didn't have to log linearize it. It's a quadratic, I believe, his original model, if I recall correctly. That Statespace Form can be thought of as this. Well, this is actually a reduced form. Remember how I said these F's, you could put in a HH inverse in here? So this, you can think about this as a reduced form. I haven't imposed any structure at all on this. There's some crazy normalization the principal components normalization or something like that. Well, if you impose some structure on this and you make this a structural model and maybe you impose enough normalization to identify it, let me put tildes on top of everything. So I'm going to call this a structural model. Well, what does a structural model mean? A structural model means that now these phi's, if I want to think about this as a structural model, or more precisely, a state space, the state space equation the state equation for a DSGE, these phi's are going to be functions of some underlying DSGE parameters, say theta. So are the covariance matrices here. These x's are going to be the things that you're going to use to estimate the DSGE. I've thrown on some measurement error. Sargent had some measurement error in his paper. He said that the statistical agencies added on measurement error. So you could do that. Or you could say, I don't like that idea, and you could zero out this term. Aside from notation, this is the model that I wrote down yesterday, right? Okay. Here's what Bovan and Giannoni did, which is really cool. Okay, what Bovan and Giannoni said is, everybody who's estimated DSGE so far has taken them far too literally. There's this thing that they call X in a DSGE. There's one X in the economy. And that one X is, I don't know, different people, somebody might think it's labor share, or somebody else might think it's output gap, or somebody else might think it's consumption growth. But there's one X in the economy. And there's one R, and there's one pi. And that's stupid. So here's what they say. They say there's a latent factor, X. I don't know. I have income and consumption. I probably shouldn't have done that. I should have, to keep this consistent with the lecture yesterday, I should have had X and pi and okay? So let's call this X. There's one thing. It's called X. It's X. It's X in those equations. Well, what's X? X is related to maybe some income growth series, or some output gaps, or some consumption series, or something like that. There's no one X that's the right X. There's a number of things that are very closely related to it, but they're just measurements that are related to it. But then there's got to be some measurement error too, because they're not the same thing. And there's one pi in the DSGE, but we know that there's a ton of different pi's in the real world. And they're all kind of related to that pi. We don't observe the DSGE pi. It's a well-defined thing. It's well-defined. It's just that it's latent. And you know, there's one R in the DSGE, and that's related to a whole bunch of things in the real world. So there's these latent variables that have multiple indicators or multiple variables that are related to them, and they're related to them in a very precise way. The way you get identification is by imposing zero restrictions in the factor loading matrix. This X only loads on certain variables, and this R or pi only loads on certain variables. This is actually, if you think about it, how many identifying restrictions do you need? It's going to go back to the same R or Q times Q minus 1 over 2. And this has got, millions of zeros in it. So this is heavily over-identified. That's a good thing, right? So you can check it out. So that's what they do. So they say we've got, the way I would, so I don't know if this is good terminology or not. I call these variables that are related to, I've called these variables that are related to the unobserved factors as measurements of them, things that are like sensors. So why do I say that? It's like you've got some latent, you're measuring a wing in an airplane, and you've got a whole bunch of sensors on it that are going to give different readings of what's going on in the wing of the airplane. And then you've got this one has to do with the wing of the airplane, and this one has to do with the engine, and I don't know. Okay, so there's sensors, and then we've got other things that are just plain old information series. Well, what is an information series? An information series is something that might actually be based on expected future values of the Fs. Well, we can think of objects that are going to be based on expected future values of the Fs, like the stock returns. So if the stock market moves, it's responding to expectations, or at least one imagines, that's responding to expectations of things that might be happening in the future. If the only things in the world that could happen are Fs, that means it's responding to expectations of future Fs. If it's a future F that is responding to the projection of the future f on today's f is going to not involve a single f, but all of these things, because it's a VAR. So the projection of ft onto ft minus 1 is going to be phi ft minus 1. So we're going to, in general, have all of the f's loading onto the stock market. So we have some sensor variables and we have some information variables. And they are identified by zeros in the sensor variable factor loading equation. And phi, the state transition equation, is a function of the deep parameters of the DSGE. And I think this is just such a wonderful idea. I think this is such a great paper. They estimate it by, these Bayesian methods. You don't have to. I mean, I'd actually really be interested in seeing this estimated just by ML, because you're using now a great deal of information to try to identify this. And if there's deep problems in terms of model identification here, then it's hard to see how you're going to be able to make substantial empirical improvements. So, in any event, they have 3 different cases. So case A is like the vanilla case where it's a medium-sized model. It's not a small model. So it's like they have 7 equations, and they just make the standard pi is like GDP deflator or something like that. And then they move on to 14 variables, and then they move on to 91 variables, a lot of which are these information variables. The information variables aren't going to help with the identification of the f's, but what they're going to do is they're going to help with the parameter estimation, and they're going to help really being able to figure out what these shocks are. And so what we have here is we have some point estimates for a number of different cases, and then posterior ranges of posterior distributions, and I don't know. That's just what it is. I guess one of the, it's these particular results are somewhat disappointing in that one would have hoped to have seen standard errors reduced substantially, but I don't think that the fact that the standard errors haven't come down so substantially here. These are, first of all, they're not standard errors; they're posterior spreads. And second of all, I mean, this is just the first paper trying to implement this methodology, and I think there's a lot of promise. I mean, if the standard errors, if the posterior spreads aren't coming down at all, it's got to be some indication that these models are essentially unidentified in some sense. Okay, so let me now go back to this. Empirical, some of the 2 sections that I skipped, which is section 4 and section 5. Okay. So far everything we've been talking about in terms of concrete empirical stuff has been dynamic factor models. And as I emphasized, I think it's a question as to whether or not the dynamic factor models are actually an empirical question ultimately as to whether dynamic factor models are the best window or the best model or the best framework to use to tackle some of the questions that we've been talking about. So what that means, it's incumbent to compare dynamic factor models to other things. So there's a number of ways to ask this. You can ask the question, you can ask, in terms of empirical assessment, you can talk about forecasting, you can talk about in-sample measures of fit, you can talk about other diagnostics. Right now I'm just going to focus on alternative forecasting methods, and then we'll come back more generally to measures of fit. Okay. So the forecasting problem that we're going to talk about is the one where we have a large number of predictors, and we're going to look at the projection of y on these orthonormal predictors. These orthonormal predictors that we're going to focus on are going to be the principal components in the empirical application, and this is the problem that we studied in terms of the Bayes and empirical Bayes estimation problem. So The frequentist problem, if you recall, was to find the estimator that minimizes the frequentist risk. Through that series of calculations, the frequentist risk is equal to the Bayes risk with the some G sub n, with the actual empirical CDF of the D's. The empirical Bayes estimator, one way to think about the empirical Bayes estimator is that you try G after G after G, prior after prior after prior, and then eventually you find one that does a good job forecasting. That's actually not how it's implemented, of course, but that's the general idea. And so the theorem is that you do that again and again and again, and eventually the G that you settle on is going to be G sub n, and by empirical Bayes you will have solved the frequentist problem. Okay, so we're going to look at empirical Bayes estimators, and I'm also going to introduce, as a general matter, a number of other estimators that have been developed in the statistical literature. And again, so I think the reason I went through all of this, you know, if you saw the macro seminar and it said, the title was Bayesian Model Averaging, Bagging, Lasso, and Hard Thresholding Forecasts of Macroeconomic Activity, most of you would skip the seminar. Okay? The reason that this is important is that these are attempts, different frameworks that are actually, at a fairly deep level, closely related, that are attempts to implement what can be thought of as empirical Bayes estimates that would provide an alternative to dynamic factor models. So let's think about this problem. I have all of the principal components here. 135. So some data sets have 135. The DFM literature has you do the following algorithm. Run by Ning ICP2 without the typo. Choose R according to by Ning. Run the regression of Y on just those principal components, and then if there's some own lags that you need, you can put those in. I've ignored that in this problem. That says that the DFM literature says we're going to impose the restriction that delta 5 through delta 135 equals 0. That might be a good restriction. I mean, you know, Gawerke thought it was a good restriction, and Sargent likes that restriction, but it might not be a good restriction, and it's an empirical question. And if it's not a good restriction, and if we're supposed to use all of the data, that actually is going to tell us a great deal. So if it turns out that DFMs don't forecast as well as these other methods that would use all of this information, that actually tells us something about the limitations of DFMs as a way to think about the world. Okay. So it's a relevant question to compare DFM forecasts to all of these other forecasts that would be using the remaining 131 principal components. The optimal Bayes thing to do if you're a plain old-fashioned subjectivist Bayesian is simply to use your own personal prior G, and that's a nice framework for thinking about it. It's definitely going to be admissible. That's the decision theoretic result, that the complete class theorem. If you are a lucky Bayesian and you happen to use the right prior, you happen to have the right prior, you'll also be the one that solves the frequentist risk problem. Hard thresholding is a great buzzword for something that you already know. Hard thresholding is you compute the t-statistic on testing delta equals 0 and you compare it to a number. Okay, so now you have another way to... AIC and BIC in this context reduce to hard thresholding. Let me tell you what false discovery rate methods are very, very briefly. So this goes back to the 10 million probes on a chip. And so I'm just going to state the problem. The problem for false discovery rates is it's related to what's called the multiple testing problem or the multiple comparison problem, if you so when you're doing this genomic DNA stuff and you have these, this is 10 million, but I understand that it's actually supposed to be 30 million probes on a chip. What you'd like to do is apparently these probes measure some sort of intensities, and you want to find the values that are big and not the values that are small. And these values that are big apparently have to do with potential. Well, actually, I know what they exactly have to do with, which is when you measure the numbers of the numbers on the probe are related to genes they normally come in pairs, and if there's a problem, if there's a cancerous problem, there might be a single one, or there might be more than one pair. They might make multiple ones, and so when you shine a light through them on this probe, there's different levels of densities and light intensities, so you can actually pick up whether you have one copy or two copies or three copies. So what you're trying to estimate is the copy number of gene on each probe, and if it's tumorous, or if it's defective, then you will instead of just coming in pairs, you're going to have multiple copies. And so what you want to do is you want to identify those sites that have multiple copies and then see if you can relate that to the cancer that you're studying. If you do it as a multiple hypothesis testing problem, suppose that you look at these intensities and you construct some sort of t-statistic, if you will, at each site, and you compare each site to 1.96, and there's really no tumors, then you are going to have, out of those 30 million sites, you're going to have an awful large number of false negatives. That's not a helpful way to proceed. So instead what they try to do is instead of controlling the false negative rate, you can control the false positive rate, which is the false discovery rate, and so there's particular methods that are done using that. The simplest of these two methods is to imagine that you have you have either the right number of gene copies or you have like 3 gene copies, and then you're going to try to distinguish between those two, and it's going to be some mixture distribution. And not surprisingly, that mixture distribution, the decision about whether you would decide this is going to be a bad one, that is with 3 gene copies, is a Bayes rule type calculation. And how do you calibrate that? You calibrate it by empirical Bayes. So it turns out that this false discovery rate is an empirical Bayes procedure, and the mathematics of that has gone through in an article that I haven't cited. There's a paper, there's some cites in an Annals paper by Efron in 1983 that's supposed to be right here. Okay, so that's another procedure that you could use. It's actually not at all relevant to us, so I'm not going to present any results for that, but it doesn't make sense in our context because our problem is just not that problem. Okay. There's another thing called bootstrap aggregation, which has to do with, I'm not going to describe it. There's a paper by Inouye and Killian in the JBES this year that describes that. And there's a really nice theoretical treatment of it by Buhlmann and Yu in the Annals. And that is not an empirical Bayes method, but it could, as I'll show you, it can turn into an empirical Bayes method by a suitable calibration of a tuning parameter. Here's BMA, Bayesian model averaging. So this is an explicit Bayesian procedure, so Bayesian model averaging was actually invented by Ed Leamer, I guess. That's the credit that I usually see. And the other reference that's often given is Bates and Granger, because it turns out it's very closely related to model combination or forecast combination. There was sort of a Bayesian model averaging. It was basically a backwater for many years where nothing happened, and then these guys invented these MCMC methods, and they could suddenly solve really hard problems. So it's been an area that's received a great deal of attention in the last decade or so. And there's a few applications to it in economics. I'm not really convinced that these are very interesting, the Fernandez-Lay and Steele applications, but the technology is good. The Coop-and-Potter application is a forecasting application along the lines of what we're talking about now. So the basic idea is that there's a lot of, you're trying to do a regression, and so here's the setup. You're trying to do a regression, and you've got 135 regressors, and you conjecture that maybe there's a true model, and the true model has regressor 2, 17, and 100, but you don't know what it is. Okay, so how are you going to come up with a procedure that's going to take into the possibility that there's a number of different models that you could be using, and some of these models are going to be better than others? Well, better than others means that they probably will have some higher posterior probability. So what a Bayesian model averaging procedure does is, in principle, it estimates all possible models, which is 135 choose 1 plus 135 choose 2 plus 135 choose 3, and so forth. So it's quite a few models. So in principle, it estimates all possible models, and then for each one, it evaluates posterior likelihood that it's true, and then you take the forecast from each one and you weight those forecasts by the posterior probability, and then that's going to give you your forecast. So that's the basic idea. You can see why when it's 135 choose 1 plus 135 choose 2 plus 135 choose 3, why it was a backwater for many years, and then when these computational guys got into it, they thought this was really fun. All right? So the computation about this is, how do you sample models? Because you can't possibly go to every model, but can you come up with clever ways to sample all these different models? And they have something called MC cubed or something like that. Okay. So here's the BMA idea, which is that you would take this thing called the predictive density is the density of y given the past data. So in this jargon, it's yt plus 1 given everything that you know up to today, and you're going to average that over all the different models. So you look at the predictive density for model K, and then you say, what's my posterior probability that model K is correct, given that, what's the posterior probability that I assign to model K given the past data? And so then the next step is you've got to figure out what this posterior probability of model K given the past data is, and that's just going to be figured out by Bayes' rule, and given a prior probability of the model. So given that the model is true, you then need to figure out what the probability of the data is given the model is true. And for that, we're going to have to do another Bayesian step. So the basic idea is, for a given model, we have a prior on the parameters, and then you have probabilities over models. And so that's the setup. It's something that is computationally quite tedious and interesting to those who find that interesting. I guess that's a tautology. It turns out that in the orthogonal regression problem, it completely simplifies, because if all the regressors are correlated, then whether variables 1, 2, and 3 are in the model, that actually makes a difference whether you would add 4. That's going to change the correlation structure. But if everybody's uncorrelated, then all of that breaks up, so you can just look at one variable at a time. So it turns out that you just get this huge simplification if you have orthogonal regressors, and those formulas are given in some papers in the statistics literature, which are cited in the literature survey. And then each variable, then the model is quite simple. Each variable is either in the model or out of the model with a coin flip. And then if it's in the model, you have a posterior probability. You have a prior probability on the coefficients. So and then what happens is that you get an explicit expression for this weighted average, and you get an explicit expression for the forecast. Now, one reason that if you read these surveys in BMA, the survey always has to start with some history thing, and they often go back to Bates and Granger, because Bates and Granger, this is Bates and Granger. If you think about it, it says I've got a forecast. Mark talked about this, where I'm doing forecast pooling, and I've got a forecast from my guy at Citibank, and I've got a forecast from the person at Bear Stearns. I was at a conference last in June, where the guy was chief economist for Bear Stearns, which I thought was terrific. It was actually there was a name tag which was printed up before Bear Stearns croaked. Anyway, you get these guys' forecasts, and then you average them together, and you average them together based on how good you think they are. And how good you think they are using the using the Bates-Granger weights is going to be based on their sum-squared forecasting performance. And if you work through all of the BMA algebra, in the case of orthogonal regressors, that's exactly the explicit expression that you get, which is that you get, it's not the Bates-Granger expression, but it's very close to the Bates-Granger expression, where you penalize people who have bad sum-squared forecast errors and give more weight to people who have good forecast errors. So it's very closely related to that. It actually goes back as sort of, it's yet another way to think about this optimal forecast. This forecast, the straight mean pooling is a puzzle. But it kind of makes you think that if historically the forecasters haven't been very different, that you might want to give them weights. In the end, they might end up with weights that are pretty similar. Okay. This Bayesian model averaging depends on parameters of priors, but you will not be surprised to hear me say that those parameters then could be estimated. So those hyperparameters can be estimated, and this Bayes procedure can be turned into empirical Bayes. I just mentioned as a digression that all of these procedures have shrinkage representations. Remember, we started talking about the failure of OLS as being a consequence of in first principles, the failure of OLS being the inadmissibility of OLS and the fact that one could construct a shrinkage estimator, a James Stein estimator, that dominated OLS. And all of these that I've just talked about have interpretations as shrinkage estimators. To be precise, we can write the forecast of Y as the product of the ith predictor times the OLS coefficient times a function that's a function solely of the t statistic. And this function is a function that goes between 0 and 1, at least in all of the cases we've looked at. In all of the cases I listed, they go between 0 and 1. And so what that means is you're basically shrinking this coefficient to 0. So they're all shrinkage estimators where you're shrinking the coefficient to 0, but that makes sense. Okay. And it also makes sense from Bayesian perspective. Remember, you've got these d's that are small, so you're going to be doing some Bayesian shrinkage. All right. Let's just give some formulas for what these shrinkage things are. All right. So finally on the list, there is one large dimensional method which which doesn't fit in this, and that's because it's a multiple equation method. Using large VARs. And so there's one paper that looks at using really large VARs with strong priors. And my understanding is that this is my reading of the paper, the results were presented for a variety of hyperparameters for the priors, and the hyperparameters that seemed to work the best were the ones that were used. And that sounds to me like one interpretation of empirical Bayes. Is that a fair assessment? I don't think you used the term empirical Bayes in there, but that's essentially what you did. Yeah. Okay. All right, so how do these perform? So this is really the test, and at this point, there's an enormous literature with empirical evidence on dynamic factor models. And I'm not going to pretend to give a comprehensive survey of every paper in that literature. And so what I'm going to say is a distillation of a lot of different results. There have been papers that have, as a first cut, looked at how well the dynamic factor models describe the data in terms of R-squareds and stuff like that. A second cut is testing some of the over-identifying restrictions implied by a dynamic factor model. I think if I remember one calculation, if you have 135 variables and you think about a VAR with 135 variables, there are something like 240,000 over-identifying restrictions implied by a DFM. So that gives you a fair number of things you could take a look at. There's also, most of the literature is focused on forecasting performance and assessment through that, and I think that that's a natural thing to do, and it's important. There's a survey by Eichmeyer and Ziegler, which is now a couple years old, but it has a pretty good bibliography in it. There's a meta-analysis in it, too. I do not think this is a very useful meta-analysis, so I'm just going to make one small digression on the Eichmeier-Ziegler meta-analysis. They use as the unit of observation a relative mean squared error, which from tables of results in these papers. A relative mean squared error is the performance of a particular forecasting method, a principal components method, for example, divided by some benchmark. The problem is that different papers use different benchmarks, and the meta-analysis takes those as data and then tries to understand the variation in these relative mean squared errors as a function of a variety of different features. But since the denominator in these relative mean squared errors isn't the same from paper to paper, I think that that's a really problematic exercise. It's a valiant thing to do, but I have some questions about that particular. I think it's very hard. I'm not sure that. I think meta-analyses are valiant efforts. They're fairly controversial for the sorts of reasons that it's difficult to combine studies in a formal way. Okay, so let me make a couple of comments. I'm going to go through a list of things. First of all, with data selection, as a practical matter, there isn't a lot of talk about data selection in the papers, but of course in practice that's an important thing to do. I think that when you're actually formulating and estimating a DFM, you have to bear in mind that the factors that you get out are going to depend upon the variables that you put in. If you put in entirely output series, you're going to get out output factors. If you put in entirely price series, you're going to get out price factors. It depends what your application is, but you have to, if you want to have a broad swath of economic factors, if you want your factors to reflect a lot of different economic features, you have to have a large number of varied different things. I think one of the issues, one of the critiques of these papers that find a very small number of dynamic factors is that potentially or arguably the data that they're using are heavily dominated by just real activity variables. So I've talked about comparison among the different factor estimation methods. I don't think that there's a great deal of evidence suggesting that one is better than the other. If I had to recommend one right now in terms of a combination of convenience and efficiency, I guess it would probably be principal components followed by the two-step ML. So that still requires you to write down the state space representation and pass it through the filter. But that does give you a lot of flexibility in terms of doing things in real time and working with messy data. There's been a number of papers that have been compared many predictor forecasting methods. I've listed a few of them here, and there's some other ones. My overall impression from those is that, by and large, these dynamic factor models come out looking extremely good. There's little evidence that any other alternative prediction method among these many predictor methods works better than the dynamic factor models, and most of them tend to work worse, some by a fair margin. So I'm going to show you just one set of results, which are results from a paper of Mark and myself, but I think they're representative and typical and give you a flavor of what's going on. And those results this is using these different shrinkage factors, and this is a mechanism for comparing a large number of different alternative procedures. Remember how I said that those things like bagging and BMA and all those things that you wouldn't go to the seminar for all turn out to have these shrinkage representations. And that means that the performance of these different procedures can all be compared just by looking at that shrinkage function. And these are just different shrinkage functions for different procedures. BIC is a hard thresholding, so for the data set we have, ln(t) over t happens to be 2.4. So if the t statistic is less than 2.4, you don't use it, and if it's greater than 2.4, you do use it. So that's a hard threshold, an L hard thresholding function. These other things have more S shapes. This thing here is for bagging, which I'd never described, so it's hard to understand what in the world this is, except it turns out that bagging has this psi function, this shrinkage function, so that if the t statistic is 1, that coefficient does enter the regression, but the coefficient is shrunk to 0 with a weight of about 0.4. Here's a green one, which is BMA, And actually, this green one is an important one. This green one is empirical Bayes. So there are two parameters to this family of priors. It's a probability P that a variable is in the model, and then there's something called a G prior tuning parameter. And so those two priors are estimated by empirical Bayes, and the empirical Bayes estimator says that if your t statistic is 2, you basically are getting very little weight, and to get a lot of weight, you've got to have a t statistic that's out in the 4 or so range. So it's actually being pretty tight in terms of how it's discriminating about what variables that it puts in the model. All right, so let me show you some forecasting, some results. And so what these results are here are their weights on the different principal components. And the principal components are ordered in terms of the size of their eigenvalues, the first being the one that explains most, so like the real factor, right? So it's the first is the one that explains most of the variation, and then number 121 doesn't explain much of the variation of the x's. The forecasting methods here are really not paying any attention. Remember how I said that the estimators are equivariant, permutation equivariant? What that means is that these forecasting methods, every one of these forecasting methods does not look at the index I. All right? It does not depend on I. There's no forecasting method that says, oh, it's the second principal component, I'm going to give it a break. Right? Bagging one works really terribly, and it works really bad, and the BMA one works really bad. This green one is empirical Bayes, and the B empirical Bayes is supposed to work well, and it does work really well. So the green one is empirical Bayes. It works really well. What does empirical Bayes put weight on? It puts weight on the first 4 factors and 0 weight on everything else. So it doesn't know they're the first 4 factors. It just says, I'm going to do the best empirical Bayes job forecasting that I can. And it turns out that this forecast is the same as a dynamic factor model forecast. And that's for the unemployment rate. Same thing for the inflation rate. It turns out the same thing is not true for the T-bond. And actually, the T-bond rate was very difficult to forecast in this exercise. And none of the forecasts really did particularly well compared to low-dimensional systems. So it doesn't work universally, but the evidence on sort of these real and nominal variables is that, in fact, it worked. In fact, what's being pulled out is, in fact, just the first 4 principal components. So this is one take. This is not looking at any forecast relative mean squared forecast errors like Mark was talking about this morning. This is looking at something else. But what it essentially says is if you ask what there's this really profound theory they're saying will produce the optimal estimators that are going to solve this frequentist risk problem, it turns out that it says DFM. Okay. So let me just. This is one other interesting thing. So this is from a comment of Mark's on a paper by Giannoni, Reichland, and Sala in the Macro Annual 4 years ago, and this is looking at the fraction of variance explained by 1 and 2 factor models for a variety of different series. And one of the things that he noticed was that this Sargent and Sims paper a long time ago used many of the same series or things closely related to the series that were used by Giannoni, Reichland, and Sala. Of course, these guys used tons of series, and this is all that these guys used. But one of the things they were able to do is they were able to use they actually couldn't extract a factor because they were using these frequency domain methods, but they can compute fraction of variance explained, R-squared type measures. And what they found is that the R-squared explained by 1 factor was very high for some of these things. So for industrial production, it was 94%. For layoffs, it was 83%. For new orders, it was 67%. If they increased it to 2 factors, the amount explained really didn't go up by very much in many of these cases. The remarkable feature that seems to be the case is that many of these results are actually still true when you look 20 years later or 30 years later and look at much, much larger data sets with many more n. You still see fractions of variance explained that are very amazingly close quantitatively to these smaller DFMs. In some cases, like the Euro guys' macro annual paper does a better job with prices. They had more prices in their system than the Sergeant Sims one did 20 years ago, 30 years ago, which didn't have prices, only had one price. The marginal gain from going from one factor to two factors, and this model was also fairly modest. So they end up concluding that the number of macro factors was very, very small. That potentially is a function of what variables were in the system. If there were more variables measuring other things like interest rates or prices, maybe you would get different answers, and there are other data sets that have given somewhat different answers to just one factor versus two factor. I would not want to emphasize the 1 versus 2 number. I'm a little bit more agnostic on that. But the indication that it's a small number is pretty, I think, pretty compelling. All right, so I think what I've done is intentionally gone fast to try to get everybody who wanted to go to the airport out. So I'm done. All right? Okay, thank you.